Not bad. Oh, grid. I love a grid problem. Okay. Go ahead and grab that. Didn't really get set up earlier. Okay. Boom. Part one done. dumpling? Let's try just a force. Oh. So I have the wrong thing copied. So maybe that did work fine. $43, that was right. That was right. Okay, let's see how long this is going to take. Not long at all. Oh, pretty quick. Like I said, I like a grid problem. Probably could have gone even faster if I just believed in myself instead of printing the input and double checking all that. Let's just clean it up real quick. And we'll talk through it. Okay. So have another dumpling and then we'll talk through it. Okay, so for this problem, we're working with a 2D grid, something I've done many times before and something I enjoy working with. We have these rolls of paper. I don't know why, while I was doing it, I was picturing like toilet paper rolls because it kind of looks like a toilet paper roll on its side. But they're just paper. Anyway. So the deal is, if there's less than 4 rolls of paper adjacent to a roll, then we're marking it as like safe to take. So the first thing we want to do is get our neighbors. I'm specifically counting the number of @ that are in our neighbors. Other times I've written similar functions to collect all the neighbors and add them into an array or do other things with all the neighbors. But this is a sort of function I've written before in a more or less a similar way. So I kind of already had a good idea of how I wanted to approach it. When I do a 2D grid problem, I like to upfront get the bounds. That can just be helpful to have. Keep yourself in bounds to iterate through the whole thing, blah, blah, blah. So I wrote this quick function, takes a row and a column. That's also something when I work with 2D grids, I like to use R and C for row and column. Just makes it easy to remember which one is horizontal, which one is vertical, not get confused with X and Y or I and J or something like that. So I like R and C. So what I'm going to do is I'm going to go from -1 to 1. I'm going to call this like delta row or difference in row and difference in column. And so if I'm at a given, let me go back to the example here. If I'm at a given square, and I know my coordinate is what, 1, 4, then my neighbors are going to be from -1, 0, +1 in the vertical direction and -1, 0, +1 in the horizontal direction. So that's why I have these little range. Range is not inclusive of the upper bound, so it's going -1, 0, 1, -1, 0, 1. And since I'm not counting the center item, I'm like, that's the one that I'm on, and I just want to get the neighbors around it. So if they're both 0, I skip over it. I'm using my difference and my input row to calculate like what the new row and the new column are going to be. This is like the row of a potential neighbor and the column of a potential neighbor. Then I'm first checking that they're all in bounds. So if my row is greater than 0, if my row is less than my vertical height of my matrix, if my column is greater than 0, if my column is less than my horizontal height of my matrix, then I know I'm in bounds and I'm not going to get like an out of bounds error by keying in here. Check the value. If the value is an @ or a roll of paper, increase my neighbor count, return the count. So I can use this function on any like coordinate row column and get a count of all my neighbors. So that's going to make the rest of this problem super easy. I'm going to keep like a total, total available to be taken count. I'm going to go through all the rows in my bounds, go through all the columns in my bound. If the coordinate, if my grid or my matrix at that coordinate of row column is a roll of paper, I'm going to get the neighbor count. And we say, according to the problem, if there are fewer than 4 in the 8 adjacent positions, that means it's accessible. So if there's fewer than 4, I'm going to increment my variable. I called it available instead of accessible. And then I print it out at the end. So simple enough. And if we do it on the example input, we get 13, which is correct. Right, so that's cool. For part 2, part 2 says, once you remove the initial set, obviously that makes more of them available because now some of these are going to have less neighbors. If you take those away, then the neighbor count of these other ones is going to go down. Right, so we do our initial remove the 13 rolls. Now we have a new one with less. They're marked by these X's of where the ones are missing. So that means now we have, 12 more roles that have fewer than 4 neighbors, so we can remove more. Now we have 7 more roles with less neighbors, so we can remove more. All right, so it's kind of just keep going, until we can't remove any more. So since I was going quickly and I just wanted to get a solution as fast as possible, I didn't really optimize it per se. I basically just simulate that process. So the code is very nearly identical. Okay, I did a little bit with the spacing here. What's off with the spacing? We'll put an extra line here. Right, so if I compare these two, all this stuff is basically the same. I did change this so that I can mutate the input for later. And I have basically the same loop here. But what I do is I wrap it in a while loop. So I use this sort of like sentinel Boolean changed to say, if I have removed any rolls of paper, I'm going to count it as having changed the state, and I need to check it again to see if I can remove more rolls of paper. So for each loop iteration, I'm starting off with the assumption that I haven't changed anything. I'm going to iterate through the whole thing just like I did before. I'm going to test each roll of paper just like I did before. If I do find a roll of paper that I can remove, first of all, I'm going to mark it as having changed sometime in this while loop iteration. So I know I have to do at least one more because I've removed a roll and potentially changed the amount of neighbors that other ones have. And then I'm going to actually change the input, which is something I almost forgot. So I'm going to replace this with a period to therefore open up the neighbor count. And that's why I did this little thing up here. Initially I had an input which was like actually a list of strings, not a two-dimensional array or matrix. So I quickly parsed them into actually two-dimensional matrix of strings of like individual characters so that I can do this. And then I just simulate that process basically exactly as it's stated in the problem. I didn't try and do any fancy optimizations or anything like that. And as you see, gets the right answer for our sample here. And it ran very reasonably fast. That was pretty quick. Probably less than 5 seconds. I don't know how long it was. I could probably time it, but that's fine. Before I set up, I was kind of thinking like, oh, we're going to have to, this is a decently sized grid. I might have to optimize it somehow. One way that I was thinking of optimizing it was like making an initial count of all the neighbors, and then every time I remove one, I can just update the neighbor count immediately instead of having to every time count all 9 or all 8 of the adjacent squares. I could kind of just like instantly know which ones I needed to do, but that honestly wouldn't save that much. It would save 8 operations per each one, but 8 is a fixed number. Again, we were kind of talking about this on one of the other days. 8 doesn't scale with the grid size. 8 is just always 8. So even if this grid is way bigger, the number of operations is still 8 per. Now it could have been long if there was like a long string and I had to go through the whole grid and just remove one, and go through the whole grid and just remove one, and go through the whole grid and just remove one. So potentially, some room for improvement, but this was totally fine for today. Got me the right answer. It's pretty quick for me. Again, I've done a lot of grid problems. Where do you find your personal times? Yeah, 5 minutes for part 1, 8 minutes for part 2. While I'm kind of chilling, eating my dumplings, don't have any scripts set up to download the input or submit my answer. just kind of copying and pasting. So not too bad. I really like 2D grids. They come up a lot in past Advent of Code years. So I've done them before. Love them. Very comfortable on them generally. But all right, that's that. Thanks for watching if you popped in. And we'll see you again tomorrow.